Okay, let's just turn the lights down here. Okay, so slightly change the order and contents of the next few lectures, basically covering the same sorts of areas, but just in sort of different order and different combinations. So this week, we're going to talk about design, and this is going to be the first of two lectures on design. We'll have the second one when we get back in week 6. So for master's students, remember there is no, well, for everybody, remember there's no lecture practical next week. It's what they call enrichment week for the undergrads, where they, I don't know what they get up to, enrich themselves. For the postgrads, you can read the, there's the digital mapping sort of module materials, which you're advised to cover in those weeks. Okay, so this week we're going to I'll talk a bit about conceptual design, and then so what we're going to cover is, first of all, going to talk about usability, the general concepts, ideas around usability of software, then go through some system development models, the waterfall model and the iterative model, and some of you who've done data management and manipulation will have seen some of these things before. Then we'll put in, see how the development stages of the conceptual, then the logical, then the physical models that you develop when you develop a web application, or indeed any application that you have to go through. So we'll map these stages onto the waterfall and the iterative model, and then finish off with discussing some conceptual design tools. And throughout this, where appropriate, I'm going to drop in some examples from that entangled bank database that I'd created in the past. It's quite a good sort of statement. Usability is like oxygen. You don't notice it until it's missing. So when you're using a bit of software that's well designed, that's easy to use and easy to operate, you don't need to think about it. You don't notice that there's a, you don't notice necessarily that it's a good bit of software. What you notice is when something doesn't work, when something is slow, when something's clunky, when something you don't understand how to do things and have to spend a lot of time trying to work out how to do it. So the sort of key to usability, or the ultimate aim or goal of usability, is to sort of get your user to intuitively use your website without having to actually think about how they, what they're actually doing to use it at a particular time. And usability really matters. We've got a couple of examples here, not computer web mapping examples, but I think they bring home the importance of usability and good design. So I don't know how many of you know have seen this thing before? Yeah, a Sinclair CS5. When I was 1984, I was probably doing my A-levels then. This was the future of road transport. It was a combination. It's basically an electric kind of buggy thing that you could also pedal, and this was meant to be the sort of the revolution of the new revolution in transport. Created by Sinclair, you may know, as the sort of man who invented sort of calculators and stuff like that. But the Sinclair C5 was an atrocious disaster for a variety of reasons. Had a short battery life. It was quite heavy, so as soon as your battery ran out of power, people find it very difficult to pedal. Had a lack of seat adjustment, lack of gears, short pedal cranks, an engine that overheated. The drivers felt grossly exposed. If you can see, they're quite low to the ground, quite small. So the drivers felt very, very exposed, and indeed there was a whole safety scare over the low driver position. People felt that there was great scares that people were about to get run over by trucks and things like that, and they're probably very, very true. This combination of poor design and the sort of press hoo-ha that went on with it the laughing at it meant the C5 had a very short life and was soon abandoned. So in that case, there were a number of design elements that resulted in the failure of what was meant to be a revolutionary commercial product. Our second example is the USS Vincennes, which on 3rd of July 1998 shot down Iran Air Flight 655 going from Tehran to Dubai, which is a commercial aircraft. The aftermath of the investigation revealed that the primary, or one of the main causes of this problem, of this plane being shot down, was a poorly designed screen interface. Basically what was happened, we had the USS Vincennes was in the Gulf. This is just during the first, I think it was the first Gulf War. The plane took off from, or came in over the Gulf of Hormuz from Iran, and because of the way the interface was designed, the missile operator or the radar operators on the ship got confused between an F-14, so they were listening to the audio of an F-14, one of the Americans' own planes, watching this dot on their radar screen, mistakenly thinking they were listening to the pilot of what turned out to be a commercial airliner, when in fact they were listening to one of their own pilots. They also didn't have integrated information on whether the plane on the radar was going up or down, so they didn't know whether this plane was in fact ascending, but it appeared they didn't know what they thought it was descending due to the audio commentary, or what they were listening to. Presumably it wasn't very good audio, otherwise they might have been able to tell whether it was an American accent or not. And they thought it was descending, and as a consequence they shot it down. So this poorly designed screen interface was regarded as one of the prime reasons for this plane being shot down. So those two things, one was the Sinclair C5, the other one being the things, weren't very usable. Their usability was their problem. So in computer systems, we've got the idea of usability. We want our systems to be usable. And the original slogan for usability was easy to learn, easy to use, very simple idea. And we can and that has been sort of expanded to identify to these four key elements about usability and things you need to think about when you're thinking about the usability of your software. So the prime thing is to think about how and why people use a product. And of course that product could be anything, but in this context we're talking about a web application. So you need to think about who your potential users are and why they want to use it. Importantly, you need to evaluate the user experience rather than simply relying on designer intuition. So you as a designer of a system have your ideas, and some of them probably very good and justified ideas about how users can interact with your system, and you can design your interface so that it's hopefully highly usable for those users. But ultimately, you won't know whether your design has worked unless you actually test it and get feedback off your users. The idea of usability has expanded from just ease of use to cover what's called the 5 E's, or the 5 E's are the 5 things that you should evaluate to measure how usable your software is. And those 5 E's are its efficiency, its effectiveness, how engaging it is, how attractive is it for people to use, how error tolerant it is, and how easy to learn. So potentially if any of those fail, the system is not usable. Perhaps it's too slow. Perhaps people don't use it because it's not doesn't grab their attention. Perhaps it's full of bugs and therefore people give up because it keeps giving them error messages and things like that. And the final one, which is also labelled number 1 for some reason, is that the design should revolve around the users. And the products that embody the user's point of view, that have the highest usability and the highest success rate. So what do we mean by that? Embodies the user's point of view? Well, different users have different mental models of how the world works, how things connect in the world, and if you design your system so that it kind of maps on top of users' existing models of the world, then chances are you're going to end up with a better product because it's more intuitively understandable. Obviously, it also you have to understand the user's goals, the tasks that they need to do, and the tasks that they have to undertake to meet the various requirements of their job or the system. Usability is also linked to what's generally called user experience, unsurprisingly. I mean, I've been trying to read some of the literature over the last couple of days, over the weekend, trying to sort of tease apart what the difference is between usability and user experience. And I think there's not a great deal, but there's a sort of semantic difference among people who are obsessed by user interface design. However, to me, the usability focuses on users in general and what they want to do. Okay, so tasks, goals, how they model the world. This user experience is as much about how you get users to engage with the product rather than what the product actually perhaps does. You can see the difference there. One is what the product does, how you go about building the product, and the other thing is, well, how do you get people interested into using this stuff? What do they gain? How do we promote software, especially when you think about software from a kind of sort of volunteer geographic information perspective? So a web-based application that lots of different users might use versus, an interface or a system that's within a company where people use it because that's their job to do it and they're paid to use it and they have no option to use it. So user experience, as we can see in this diagram, user experience stroke usability, draws on knowledge, information and techniques from many different aspects So we've got elements of computer science, ergonomics, graphic arts, software design, etc., etc. And your user experience, so how do you get a person interested in using a piece of software? Well, there's a whole variety of approaches. But one of the things that's kind of in vogue at the moment is to try and make software fun to a certain degree. And have you heard the term gamification? Which is the idea that you take concepts and ideas from computer games and try and use those techniques and applications in your software to try and get people to use it. So for example, if you're on something like, Stack Exchange, where people post IT questions and people post answers, those people who post answers to questions get points, basically. Get a points, and that sort of, they get awarded medals and things like this, which shows how helpful they are as an individual. So to a certain extent, there's a degree of competition. Who is the number one person at answering questions on Stack Exchange? So there's an element of competition, but there's also the element of just monitoring how well you are doing compared with other people. I'm a gold star answerer of questions on a particular site. The user experience covers many different aspects. For example, well-being. You're using computer software, you're sitting in front of a computer for 7-8 hours a day. Potentially, how do your user, there's a real health and safety issue there. repetitive strain and stuff like that. So how do you design your software to prevent or reduce, minimize things like repetitive strain injury? Number of other issues, I won't go through those in great detail, but you can see that these are sort of what I would say are softer aspects of the design side than perhaps the usability slides indicated earlier. So, we aim for usable software. And the question is, what tools can we employ to help improve usability design? And that's basically the purpose of this lecture, and the next one is to run through some of the tools that you can use to help, hopefully, improve your design, usability design. And to consider the tools, different tools have different applications in different steps of the design process. So the first thing we have to do is just simply consider the system development process as a whole. As I say, some of you will have met some of this before. So the first thing we'll consider is the waterfall development model. So this is a linear model of development, software development, which in fact originates back in, I believe, the mid-1950s and comes originally from sort of process engineering, systems engineering within factories and stuff like that. And it's basically when computer systems were starting to be implemented on mainframes in the 60s, 70s, often you were creating things de novo from the first time. So this model became generally taken up. So it's relatively simple. You don't have a computer system. You think you need to implement a computer system. So first of all, you want to decide what the requirements of that system are, what you want it to be able to do, and for whom. So you have to sort of have an overview of what the system is going to do and what you want it to do. It's all very well having those requirements, but is it in fact feasible to do? Is the technology there to do? Is the manpower there to do? Do you have the money to do it? So it may be that it might be a good idea and you've got a system that you want to, that you've got a set of requirements that you'd like to implement, but it's just simply not possible given the organizational structure. Maybe it's too big a job. Maybe it requires, maybe it's too expensive. Presuming you get the okay and it is feasible to implement your system, you then need to design it. And that's obviously primarily what we're interested in. You need to design the system. Take those requirements and decide how you're actually going to implement those requirements. Once you've decided on a sort of intermediate sort of design, you actually have to go away and implement that design using a particular set of software. So you have to construct it in some type of software. Once you've constructed your piece of software, you need to test it, because you don't want to send out a piece of software full of bugs into an operational environment. That could be hugely embarrassing and very costly. So you want to test what you've built, presuming you fix the bugs identified during testing. Then you want to implement that system throughout the organization or wherever you're implementing it. You get the system up and running. You get users using the system. Then you want to review how well the system has met its requirements. So how you review the system on the basis of how well the system meets the original requirements. So it's a very linear model, straightforward. You start with something, an idea, you end up with a product, and then you review the product at the end. Now, once you've got a system up and running, then clearly chances are you're going to want to change it at some point. You want to add new functionality. And so really that system, that linear model there is rather unrealistic. The reality of the world is that you build a system, you design a system, prototype, you design a system, then you want to add new functionality to it. So it just becomes a cycle. It's not just a linear process, it becomes a cycle. So it's a constant, you turn into an iterative development model whereby you're constantly designing, adding new functionality, testing that functionality, ultimately refining your design, putting it out to your users, evaluating it. You end up in a circle. Now the reality is, of course, well, this is a diagram from a sort of etching of M.C. Escher. So the idea is you've got the linear flow. Here's your waterfall, but you've also got a cycle as well. Okay, so you have both the linear component and the cycle as well. So those are very kind of, I would say, physical models of how software development goes on. It's about what you do, the stages of what you do, and the order in which you do those particular stages. But there's a lot more to software design and implementing software applications than simply having a sequence of tasks that you have to undertake and complete. You have to have a team of people who are capable of implementing that design, those requirements, who have the skills to turn those requirements into a sort of general fuzzy requirements, conceptual requirements, into an actual software product, a logical software product. I just want to briefly introduce the Agile Manifesto. So these kind of semi-rigid, so the iterative design and the waterfall model were kind of relatively, what's the right word here? Fixed ways of doing things. You followed the waterfall model, you did your requirements, you did your feasibility, you did your design. It's you automatically follow that process. Going down the wrong way. We recognized with the iterative model that, in fact, we keep doing this often, that software continually develops through time, and therefore we go through multiple cycles of the waterfall model. The Agile Manifesto says, well, to succeed in doing this, we have to have teams of people with the right skills. And it's not that the Agile Manifesto is not another model of steps that you have to go through. It's more of a sort of general overview of the type of the working environments and the personal interactions that allow you to actually complete the software development cycle. So, and they have a sort of, the manifesto, basically it's just emphasizing sort of certain things. So, for example, they say individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contracts and negotiation, responding to change over following a plan. Okay, so those are the sort of headline things. And what do they mean by those? Well, they're more understandable if you read these 12 principles of agile software design. And I'm not going to go through these in detail. You can look at those in your own time. One of the most important things, I would say, from the agile perspective, is maintaining communication between users and managers of the people who want the product and the people developing the product. What happens all too often is that you have a meeting, you have a requirement, you have a group of people who set up the requirements for a software project. That gets handed to the developers, who then go away for months on end, spend their lives doing computer coding in small rooms. Then 3 months later, 4 months later, they come back, they show what they've made to the people who commissioned it, and of course they've made something different to what the people, because of a misunderstanding somewhere along the line. And it's only through maintaining communication, constant communication between the users, the future users and the developers of the software, that you're actually going to get the best results. How do you maintain communication? Well, clearly having meetings is one of the most important ones, and most importantly, face-to-face meetings. not sending things by email, not communicating necessarily by email. Of course, you communicate by email, but there is no substitution for personal meetings. The other thing is to produce software releases kind of on a regular basis, so that you're constantly, so that the people commissioning the work, the development, are seeing how things developing on a week-by-week basis. It doesn't matter if those things only do a small amount of the application, if they're full of bugs, it doesn't really matter, but it maintains that communication and dialogue between developers and users. Okay, so this covers, to a certain extent, a lot of the soft side of the team building, the communication between developers and commissioners of work. Things like simplicity, trying to get rid of boiling down to the essential functions of the system. Anyway, I'll let you week through those in your own time. Okay, systems engineering. So you probably heard these. You should have likely to have come across these three types of design in the past. So the idea of conceptual design, logical design, and physical design comes from the systems engineering literature, rather than perhaps the computer. Computers are just one example of systems. And this division of implementation, of the implementation cycle, divides into conceptual design, which is basically the high-level business functions and requirements part of a systems development, where you identify basic abstract entities of a system and the relationships between them, and that's what this lecture will be about primarily. And then the logical design, once you've got a conceptual design in place, then you can start developing the logical design, which sort of further defines the specific entities and their attributes and their relationships of the system, but without any implementation details. So the conceptual design is a high view overview of what the system is meant to be doing. The logical design says, how do we turn that, because computers are purely logical, into a logical system of objects, entities, attributes, and relationships. And then the physical design says, how do we take this logical design and implement it in a specific set of technologies? Okay, conceptual design, logical design, and physical design. So how does that map onto the waterfall model, or the waterfall with the iterations stuck in? So first of all, we've got our waterfall model here, and then we've got feedback. We've got our feedback loop from our iterative model, so we learn something from review, we can feed that back into requirements, we can feed that back into design, we can feed that back into construction. Unsurprisingly, the conceptual modeling covers particularly the requirements stage, but from my experience, it kind of bleeds into feasibility and design as well, because there's constant, as I say, there's constant feedback going on. The logical modeling side is mostly what you call the design component in the modeling, in the waterfall model. The physical implementation, unsurprisingly, maps onto sort of the construction phase. But as I say, there's quite a bit of, because there's feedback, these divisions are rather fuzzy in my mind. So we're going to deal with, in this lecture, on the conceptual component. So there are a lot of different things that you must design in a system. And one of them that we saw the last couple of weeks is the system architecture. Somebody has to decide what the architecture of the system is going to be. What software components and hardware components do you need to put together in what particular way to meet the requirements of your system. There is the data model, the database model, how the data is structured within a database or some kind of flat file system. That must be designed. Potentially you're designing a database schema to store your data in. You have to design the programming logic. If you've got JavaScript programs running, PHP programs, that logic program has to be designed. And then there's the interface that the users use to to interact with the system, and also that provides the feedback, the results returned from the system. So there's four things, and there may be other things that I haven't thought of that potentially need to be designed in any application. And there's a variety of tools that can be used in these different design stages to help the design process, and hopefully to result in a usable system at the end of the day that actually delivers what the users actually need. And I've got listed a few of them. These are just the ones that I was intending to sort of speak about. So this week, we're going to deal with the conceptual books at the top. So we're going to look at conceptual system diagrams, human-computer interaction, scenarios and storyboards, use cases, and paper prototyping. So that's the rest of this lecture is going to be back. And then on the week after next, we'll cover the logical and physical modeling components sections. All right, conceptual design. So as we've already mentioned, systems that do not meet user requirements in an accessible way often fail. If your system doesn't do what users want it to do, they simply won't use it unless they're forced to do it by their employer or something like that. So the aim of conceptual design is effectively to identify the organizational requirements, the user needs, and the means by which to deliver the user needs and requirements. And that's only, when I say the means, it's only in the most general sense. So are we going to get a computer system, or do we want a hard paper system, for example? And the other function of it, the conceptual design, is to explain the needs and requirements to the decision makers. Because at this stage, often you're in the stage of deciding what a system is going to be and what it's going to do. And this is to justify the cost of implementing the system. So you need to be able to explain this to the high-level decision makers, the money people, who often have no idea about this and simply do not care about the technology that underlies the system. They want to know, is it going to make me a profit? Is it going to increase my efficiency, the efficiency of this organization? That's what they're interested in. They're not really interested in whether you're using MySQL or Postgres or which library you're using or open source or not. They just want to know, the bottom line is this going to improve our system? Oh dear, that's a great diagram. Okay, so conceptual is one of the, it's a shame that slide's not working very well. So one of the simplest things to do is to draw a conceptual design diagram. And that is simply a diagram that illustrates the overall function of the system. Now that was my entangled bank, one of my entangled bank diagrams. You'll have to look at that on the slides. But basically, no, it doesn't show on that. Oh dear, never mind. We'll just ignore that one. We've got some other examples. So you saw that one last week. That's a kind of conceptual. It's a bit more detailed than you'd have in your average conceptual design, but it shows the basic thing. We've got our database. We've got an interface. We've also got a way in for other people, for experts to access the data in the database, and we've got an interface that general users can access that information. This slide here had Homer Simpson in the middle, and it was showing the various data types that he could access, very simply. Here's another example. So this is an example from Esri, and this is an emergency incident web app. And in this case, we can see we've got information coming in from helicopter and ground vehicle locations. We've got information coming in from about highway incidents, highway speed and photos potentially, hospital status. We've got base maps potentially. We've got geocoding services. Somebody calls in and says there's an incident. I've just seen there's a sort of a pile up on the I-65 just 5 miles north of somewhere. Then you need to get the coordinates for that location through a geocoding service, and this information is combined into a mashup in a web browser. In this case, using ArcGIS, JavaScript API, and JavaScript. So this is an overview of what this system might do, the information it uses and how it's fed through GRSS and other systems to your viewer. You can see these are general, very general. Here's, I'll go down and do this one first. This is another Esri one. Notice that Esri have a kind of house style. You know, when you go to Esri and people ask for they commission a requirements document from Esri for their potential application. Esri create these. They write a report about whether it's a good idea to implement this system or not. Here's another example. This is Rhode Island DOT Enterprise GIS Architecture Conceptual Plan. So basically this is another, the details of course don't really matter, but the important thing is it's showing you the various sets of information, how the various bits of information are connected to, the fact that you're bringing in data from contractors, you're bringing in data regarding the health infrastructure, workflows, etc., etc. So these diagrams provide an overview of how the system operates, where the data is, what the various data suppliers are, how it's brought together for a display. Very general. Here's another example. This is from our ex-colleague Edgar Somasundra. And this is, it's not actually, this diagram isn't in this article on health and place, but he drew this diagram, I think it was included in a previous draft, and then the reviewers presumably said, we don't think this diagram is necessary. But this is for a health portal, which is meant to automatically notify people when there's an earthquake as to whether it's likely to be there's going to be a health issues surrounding the earthquake. So we've got we saw the early warning systems for earthquakes from, for example, the USGS, providing these RSS feeds. So this is where there's an earthquake. An earthquake has just happened here. We also potentially need to know, well, if it's in the middle of Antarctica, nobody lives there. It doesn't matter from a health perspective. If it's in the middle of a desert where there's no population, it doesn't matter. But so the United Nations has a whole register of disaster risk to do with things like what's the population density in this location? Is it an area that's susceptible to landslides? Large earthquakes trigger landslides, cause larger trouble. So if it's an area prone to landslides, which has just been hit by an earthquake, and it's also got a dense population, potentially there's a larger health risk. The other thing is the third source of information is the International Health Hazard Volcanic Network, which is a database of information on protocols and public health response information, depending on what different events, characteristics of different events. So we know the earthquake and how big it is. We know the characteristics of the location. And then we have information about what to do under various situations. And the idea is to bring this information together and to feed that information out to health professionals. The important thing to know about all these diagrams is that they're very high-level conceptual diagrams of how systems are, what the data is, how the data is connected, who it's supplied to. And that's about the level of detail that you want. And that's all we're really going to say about conceptual diagrams. There are no rules for drawing them. You draw them as you see fit. The idea is to communicate that information. Can you hand that sheet over to your decision maker? Does that one sheet provide enough information for them to say, yes, this is a good idea, or no, this isn't a good idea, to give them a picture of what the system is doing? Okay, so we're going to run through a number of, so that's our first tool, just simply a conceptual diagram. Now, it's a big problem how we make things usable. In the 1970s, So we're going to go back in time now a bit. In the 1970s, the only people who used computers were professionals in white coats in those days, with large mainframe computers, and a few dedicated hobbyists. Really, those was a very small user base. And frankly, how usable the software wasn't really that important. The important things at that point was, can we actually write databases? This is sort of pre even relational databases, so you're actually building the systems from the scratch in the start. In the 1980s, personal computing came along, and that made everybody a potential user. So suddenly your user base had gone from a few experts to everybody just about. And using lots of different things, bits of software, text editors, spreadsheets, games started coming in. And this highlighted the need for usable systems, because you now had a huge varied user base, not just experts who are happy to play around with command lines and plug bits of hardware in themselves. And from this developed the human-computer interaction, which is a branch of cognitive science that tries to apply sort of the principles of psychology and physiology, linguistics, computer science, and graphics to design systems that are usable for people, most usable for people. And one of the most important changes during this period was the change, as I say, from command line to the messy desktop as we know it. So pre-1984-85, before the Apple desktop, all computing was basically done on a command line like this. Along came the Apple operating systems in 84, and then Windows, I think the first Windows GUI was 85. We moved from this command line paradigm to a system of desktops, windows, point and click, programs and with programs and documents mapped to arbitrary icons. So it was a major change in perception and the means of interacting with computer systems. I think this is now changing. This model is now becoming slightly obsolete now. It's still around, obviously, but as you get more and more stuff on computers, these windows become more and more cluttered, and we're now moving more towards a paradigm which emphasizes search and sort of brushed pages with various apps on sort of multiple desktops. But now we're changing to a sort of search approach rather than scanning this complex visual environment for the icon that we particularly need. So what is HCI? Well, HCI attempts to kind of quantify, as the way I understand it, the various steps and processes that humans go through when interacting with systems and computers in particular. So this is a conceptual diagram of HCI, human-computer interaction. So, for example, we've got our manual motor processor, also known as hands. We've got a vocal motor processor, speech. So you can interact. You can tell a computer how to interact through your hands, moving the mouse, touching things on the keyboard, but increasingly you can speak to computers. I mean, back in the 70s, this was virtually impossible, but nowadays this is standard things. Potentially, you can get information back, tactile information back. It doesn't have to be visual, it could be tactile, especially for things like games. I'm not a game player, but I imagine they vibrate and do things like this nowadays. I mean, certainly when you go to sort of 3D entertainment places and you get a vibrating seat, for example, I've experienced that as well. So we've got these various bits. What happens to it? We get this information coming in, it goes into your brain, it goes into working memory in your brain. What does the brain do? Well, the brain has to process that. Some of it gets put through to, or the input gets mixed up with information retrieved from your long-term and your short-term memory in your mind. So what it attempts to do, human-computer interaction, is to take these processes our physical interactions with computers and tries to quantify them. So, for example, the model human processor is an early attempt to actually quantify these various processes. So things like how much information can you communicate to the computer through your hands? How fast can you type? How quickly can you move a mouse, for example? And how much information can you transfer from yourself to the computer in a given, under various circumstances? How much information comes in through your mind, through your eyes? How much of the information that comes in through your eyes can get processed in your brain? So they actually try and put figures through that. And here's an example. Here's a sort of more concrete example of a HCI or a model human processor model. So I don't propose to be an expert at this in any way whatsoever, but here's your senses. You've got your senses detect information, bring in various types of information. It then gets processed. Maybe some of it gets stored, some of it goes to working memory, long-term memory, cognitive processor, etc., etc. And you can actually put figures on these various steps, and then the idea is you can then model your system, what the system that you intend to implement, and you can use these figures to process, to kind of quantify how much information goes through the system, through the human system. How much of what you're putting, are you overloading your human system using your computer system, for example? I'm going to leave it at that because I'm not an expert in that in any way. And to be honest, I don't think it's used a great deal in, well, I don't know. Put it like this, it won't be used by many companies developing computer systems for use in the wild, so to speak. What it will be used for is by academics interested in how much in the psychology and the information flow between computers and human beings. So that's our second one, the human-computer interaction. That's the second tool. The third tool, and this is what you're going to be doing, is user scenarios. So so as part of this module, you need to build a web application for some purpose. So when you're building your web application, you need to decide who your users are, and what they might do with the system. So one of the things to do is to develop user scenarios. And user scenarios are descriptions of a person's interaction with a system, with the emphasis on the user's needs over the business requirements. So you're not saying from a perspective of the business what we'd like the system to do, but you're standing outside that and saying, I'm a user, what does the user want to do? And the most important way of developing and understanding and communicating user scenarios is through storyboarding, the development of storyboards. And these can be done both verbally or in text, but are more likely to be done as effectively cartoon sketches. So for example, there we've got a text example there of a storyboard, a scenario. It's a Friday afternoon, Joe is flying from Sydney, etc., etc. And here's a similar storyboard, but it's not the same story as on the left, I hasten to add, but provided as a sort of cartoon of, sequential cartoon of the scenario. And this is the stuff that's done when you're making a movie, for example. Storyboarding is integral to constructing movies, to devising plots, angles of cameras and things like this. This is a very common thing to do. So I'll go into storyboarding a little bit more, because part of your application, when you're doing your application, you've got to create a storyboard for a number of users for your application as initially part of your requirements analysis for your web application. Okay. So Truong et al. 2006 did a little analysis of storyboards that I thought was quite interesting. They looked at the various elements on a storyboard to decide how best to create these things. What's the best story? How can we make the best storyboards? How do we design? What are the design principles behind making a good storyboard? So they examined things like the level of detail, the inclusion of text, whether to use text in your storyboards or not, whether to include people and particularly emotions in a storyboard, how many frames to use, whether to implicitly include time or not. I'm just going to run through a few of these. So what they did was they drew a number of alternative storyboards, showed them to various people, users, got the users to feedback their interpretation of that storyboard. So they tried detailed storyboards with lots of extraneous information versus simple storyboards. And perhaps unsurprisingly, the simple diagrams tended to communicate better than the complex diagrams. Not surprising, extraneous information, because if you think back to your human-computer interaction, there's all these extra stuff here. The brain is having to filter those out, process them, filter them out, ignore them. So keep things simple. So your storyboard should generally be as simple as possible to communicate the information without all this artistic detail added on. Text. Well, we can provide just a picture storyboard at the top, or we can have a text description as well. Well, they found that, unsurprisingly, it improves understanding, but text is potentially has lots of bias. If you know about the idea of leading questions. You can ask a question or make a statement that, because of the way the words are put together, makes people think in a particular way. So you have to be very careful about what text to use, because if pictures are a lot more neutral than text. So if you put a particular way, you may introduce bias in the user because of the words that you particularly use. But ultimately, you're just repeating the same information. So it's unnecessary. So their advice was generally to minimize the amount of text, because you've got the danger of bias. But text can be useful when you specifically have difficulty in communicating something in a sketch image. How many panels? Okay, so they got some novices and they got some experts. Novices just being students, experts being people who work in the design industry and do this as a job, to draw sketches of the same potential requirement, the same user scenario. In general, the novices, these are actually round the wrong way. B relates to novices. Novices in general used more panels and put far more detail into their drawings than the experts did. So that kind of confirms the idea, the previous one, that less is more. Experts tend to draw simple diagrams with not much complexity, whereas novices drew far more detail. They thought the user, or the more information was required for the reader to understand the scenario than they actually required. The experts tended to break down the complicated scenario into smaller concepts, which actually required fewer panels to produce. So there was lots of extraneous information. So keep things simple again. And most experts use 2 to 6 panels. So any more than 6 panels in your storyboard, and you're probably giving far too much detail. Probably 3 or 4 is an optimum number on average. Time. There's no point in having absolute time unless there's something really relevant, whether that time really makes, whether time actually has absolute time is really relevant. Emotions. Some people, so emotions were split, I think. Some users like emotions because it makes them think gives them a connection to an application. Why should I care? In this case, it's to do with babies and safety. This has an emotional response. I think this is, the child crying is a very powerful emotional driver. But the downside of it was that emotions led people to focus on the use of the system, what the system is being used for, rather than what the system in general can do. So it may be that it grabs people's attention, but their attention is kind of skewed towards the picture itself rather than the sort of more general message of the picture. Often systems have multiple users. So here in the storyboarding, we were taking the story of one user. Many systems have multiple users. And a use case diagram, of which this is an example, is a way of just contrasting the different sets of users and their needs. So very simple, we've got a number of different users. We've got an information requester up here, an intermediary, doesn't really matter who they are. But just simply using bubbles, showing the different uses, the different things that they want to do on the system, and it's quite an easy way to contrast various users and their needs on the system. That's a use case diagram. Oh dear, I've had bad luck with my cutting and pasting. That's a bit unfortunate. Okay, EBDB, the Entangled Bank database use case. That was about all I ever did for a use case. So there was no storyboarding involved when I built the Entangled Bank base. But what we did consider was that this is kind of pseudo SQL. So if you remember the Entangled Bank, it's a database of evolutionary trees, taxonomy trees, ranges, abundance records for mammals and other organisms. So this is kind of our use case. Somebody wants to return time series as a CSV file. They will want to return a set of traits, organism traits as a CSV file. Perhaps they want ranges in KML format. And they want that information for all the species that are the least common ancestor. LCA is standing for least common ancestor of a certain organism within the phylogeny. So basically that's saying, for example, if I've got a set of species and I want to get information for all the species that those species share a common ancestor for. Don't worry about the details. Where, in this case, the taxon, where for rodents, we're only interested in rodents with a body mass of greater than 35 grams, where their range overlaps a particular spatial bounding box, and that we have time series information between 1900 and 2000. So that was one example of what a user might want out of our database, out of the Entangled Bank database. So that's simply use cases. Paper prototyping. So paper prototyping is a way of developing and designing interfaces, not surprisingly. And it's just a quick sketch of the proposed interface. Often hand-drawn, but also maybe drawn on computer. And basically the purpose is to show the main components of your interface and how they relate to each other, but we don't need any of the fine detail. And they're very good for showing static pictures of what your interface might look like, but obviously they're not very good at saying, well, what happens when I press that? What happens when I pull this down? What happens? So it's not very good at showing interaction, but it's a good way of experimenting with layouts, and I thoroughly recommend this. Here's a number of examples. The styling varies greatly, so you can go from, you might start with something like that as an initial design, and then when you've got the basics laid out, you maybe pass that over to a more professional graphic designer who maybe knocks up the next level of detail, takes that initial sketch, puts some shadings on it, adds a little more detail, and produces these a sort of more detailed paper prototype. And here are two examples, one for a system called Ember, and that one for something called Nationwide NASCAR, whatever that is, something to do with racing cars around in circles in America. Sorry? Yeah, it's southern US, isn't it? But here we've got a couple of examples, so that's giving a slightly richer view of your potential interface. So, at one point, when our funding was in danger of being removed, I had to produce some mock-ups of the interface that I thought I would build for the entangled bank, and this is what I produced just in PowerPoint to show to my the masters at Natural Environment Research Council, so they gave us some more money to carry on developing the system. So the idea for the entangled bank originally was to have a pane on the left-hand side that allowed you to select various data sources that you wish to query. So range maps, trees, tabular data in the case of the Pantheria, which is the traits database for mammals. We want to apply various queries onto those data sources. So we might want to undertake a query across a tree, we might want to query a table, and we might want a geographic query. So there's different types of queries, and we might want to combine those queries. In this case, we've got a string of 3 queries, a tree query followed by a table query, followed by a geographic query. Yep, because that's kind of what, remember the use case. The use case was give me rodents which are 35 grams or heavier. Well, that would be our potentially our table query. Got a results section here, which is telling us, given these queries, what data have we got that meets those criteria, criteria. And then perhaps we want an output tab down here that says I want to what formats I want to extract the data out. So we've got the results, I want to return the result, I want the data, I want my trees as a Newick format, doesn't matter, I want my ranges as a shapefile, but potentially it could be a KML. On the right hand side, the idea was to have this constant between all types of queries, and then on the right hand side to have specific interfaces to do with the different types of queries. So this was the spatial query. Unsurprisingly, we've got our map in the middle, we've got our list of sources of various spatial data sources at the top there. We've got the fact that it's a geographic query, various things like are we performing an AND operator or an OR operator on previous queries, that kind of stuff. What kind of base map we're using, adding bounding boxes. Do we want to upload a shape file to search on the basis of a shape file, that kind of stuff. So that was what I drew up. This is the reality of what I produced at the end of the day. So clearly, I didn't manage to, my mock-up didn't match onto the end result. Now, there were several reasons for that. One is just run out of time. And the other thing is, when you actually start implementing things, you realize that perhaps what you'd thought was a good idea, perhaps wasn't practical as the development went on. So we saw this the other day. That's the basic mapping interface. We've drawn a polygon around South America in this case. We've got the various components. I won't go into the details of these, but you can see that mapping interface is in fact different, slightly different. It's got the essential components on from the sketch, but it's not exactly, they're not arranged in exactly the same place. And most importantly, that sidebar was never implemented. So the idea was to have this as a constant sidebar and then to change this component. The reality of it was I never got round to that, while I would like to have interfaced it. So what I ended up with was a separate page with just the geographical query component, and the rest, the stuff that's on the left-hand side here, was integrated onto the main page. So this is the main interface. So this is the place where in this case, here's a list of my queries here. So I want to undertake a geographical query. I press the button here. That opens that geographic interface. You put in the query for a geographic query. I can also, if you click here, you can go into the tree interface window. If you go in here, you go into the attributes, tabular attributes query. We build up a set of queries. So instead of having a list of queries on a pull-down menu there, I've got a list of little icons that grow across the screen there. So there's a geographic query, there's a tree query, and they're using a Venn diagram, different Venn diagrams to show how those queries are connected. So this is an intersection between a tree query and a geographic query. When we say an intersection, what it is a set of names. So the geographic query, so we do a search around South America, so that will return all the data, or a list of species in South America. The next query is a query for all rodents. So this query, so we're doing an intersection of all rodents and all species in South America, which gives us all rodents in South America. Okay. The cross just deletes it. And this is sort of a summary of the results, saying that we've got 463 species which are rodents that live in South America. Okay. The output, similarly, is down here. I can add an output. In this case, I've added a table, an attribute table, a geographic. This is return shape files of the ranges, and that will return a tree model. So I've got, despite the fact that my mock-up, I drew my mock-up, the result was not quite the same, but you can see that the main components are there. They're slightly different, arranged in slightly different ways, but they're still there. Right. So for you're making your home page at the moment, and now you should be starting to think about your web application. So now is the time over the next week is to start thinking, well, what am I going to make for my GeoWeb application? So it's time to start thinking conceptual models, for example, of your web application. What is your web application going to do? Well, that's up to you. You can have it do anything you like, but it's got to have a purpose. You know, that purpose to a certain extent could be fun, but you need to think about what the general concept of the idea is and who your potential users are going to be, and start drawing up some storyboards, 1 or 2 storyboards for different users. I think I asked for just 2, or I might not have actually specified the exact number. So that's your kind of the position you should be now in. You should be starting to think about, well, what kind of application would I like to create? And you've got the examples. I posted up those examples from last year. Find a coffee shop in Kingston. What else was there? There was find the nearest place to buy bread and things like that in Milton Keynes. A whole variety of different applications. So you should be starting to think about what you'd like to kind of implement and start drawing up conceptual and storyboard diagrams. I'll just stick this up just right at the end here of this lecture. Web design. So this is kind of jumping ahead to a certain extent, but I thought this was just a few 10 simple rules of web design that I thought might be quite handy now while you're making your home page and things like that. The most important one, I think, is number 10 at the top here. Simple is beautiful. Simply cramming too much stuff onto a page is going to give your users trouble. Keep things as simple as possible. And that's probably the most important thing to think about your designing your web pages and your map application. Whether I succeeded with mine is I don't know. In some ways I think it's quite good, in other ways I think it's not so good. So simple is beautiful. So try not to be too bright. Try and keep things relatively straightforward and uncomplicated. We can go through it. No need to go through this, but design is paramount. Okay, so that's almost a sort of tautology in it, meaning itself. Is to make what they say is make a good impression. The look and feel of your site is the first thing your visitors will notice. So basically it's saying sort of it makes a difference. When people arrive on web pages and things, often you have a second or two, they clicked on Google on the Google list of returns, you've got 30 seconds or something to grab their attention, otherwise they'll go and look at the second result. So unless if your first impression in that 30 seconds is of a muddle, then you're going to lose an awful lot of users. So try and keep things obvious. So when a person comes to your page, they know pretty much exactly what it is. Have a nice title so it's clear what the page is actually about. Navigation should be intuitive. Consistency is key. Again, I'll just let you look at those things. No need to go through those in detail. Although I want to highlight number 6, colors are crucial. One of the most off-putting things about going to any one web page is super bright colors, flashing icons, unnecessary, what? Sorry? Unnecessary animation, yeah. Avoid it. Generally, keep things calm, keep things unclashing colors. Fill the browser window. I mean, these are all good things. Fill the browser window. Increasingly, you get these full-screen browser applications, and they're very good to use, I must say. That's something I sadly failed with. Develop for multiple browsers. Okay, for your web application, I'm not asking you to do that, but in a commercial environment, that's very important. Check your website for errors. You don't want error messages coming up. You want the systems to work. Write your own code. That's something that might be relevant to you. So last year I had one student at least who took somebody else's code and tried to build upon it, and they ended up with a lot of problems. Because if you write your own code from scratch, you understand it completely as to how it operates and what it should actually do. If you try and take somebody else's code and hack it to change it to meet your needs, often it takes longer than writing your fresh code yourself. That's not to say that hacking other people's code isn't a good idea sometimes, but it's a danger. You might think you might be able to change it a little bit to get it to do what you want, but you might find that it actually involves a lot of refactoring of code to actually get it to work properly. And okay, so we've gone through the system design models and philosophies, the waterfall model, iterative model, and briefly agile design. We've looked at how the conceptual, logical, and physical models are fitted into the waterfall model in particular. And in the next lecture, we'll go through the logical and physical modeling component. And we've looked for a few of the tools for conceptual design. So conceptual diagrams. So for yours, I'm expecting a conceptual diagram. We're expecting a use case or two. We want to know who the users are. We're expecting a sort of storyboard implementation of a use case. We're going to expect some paper prototyping of your interface. We're not going to expect human-computer interaction analysis in any way whatsoever. So I'm expecting to see all these things as part of your development. And part of the web application, part of it is to show the development process of your software. It's not just producing a wonderful working application at the end of the day, which is of course great, but it's showing that you understand and have gone through the steps, the design steps required to create this wonderful thing at the end of the day. Okay, so that's really important that you demonstrate how your design changed as a result of using these various techniques to first of all decide what you're going to do, then to design your interface and how that actually changed. And if you saw with the EBDB, there were some practical reasons why my interface, the finished interface, was not the same as the prototyped one. A lot of it was simply time and knowledge. And just that 10 list of web interface design principles just at the end there.